Welcome back, Chemistry 30. So we'll take a look at the rest of this. So the shift in electron density towards a more electronegative atom in a bond can be seen in the results of calculations in terms of energy, electron density distributions. And for those three species there, we can kind of get a visual picture of what it would look like. So you can see in the F2 what this represents now. So they look like big globes around the nuclei. This area, or this green on my sheet, just represents the probability of finding the electron or electrons. So we can see the probability of finding the electrons is in between the two fluorine nuclei, maybe over here, but you can see it's a symmetrical distribution. Whereas if we look at HF, which is polar covalent, we can see that, yeah, the electrons tend to be over here in fluorine's area, especially in the red area. Okay? And then with LIF, the electrons are really over in the fluorine distribution. And of course, this one's going to be ionic, so chances are fluorine's going to pull the electrons completely, and these will just be held together in a lattice structure. So we can see F2 is symmetrical, HF shifted towards fluorine slightly, and then over here in LIF, which is ionic, extremely over, completely over. So these examples illustrate, therefore, that the greater the difference in electronegativity between the two atoms, the more polar the bond. Okay, if you look at this example here at the bottom, based on the differences in electronegativity, how would you characterize the bonding between sulfur dioxide? Do you expect the bonds between the S and the O to be nonpolar, polar covalent, or ionic? So if we look back here between S and O, okay, so S has a value of 2.5, O has a value of 3.5, so we can see the difference there is going to be 1 on the electronegativity scale. Okay, so yeah, all I did is just pull those from the electronegativity scale. So if we kind of compare that to what we had here, our 1.0, so obviously it's going to be maybe in the polar covalent area. Not large enough to be ionic, but there is a difference there, which means it's not going to be nonpolar. It's definitely going to be polar covalent. Okay, so that tells us that yes, it's greater than 0. It's not a really large number though, therefore simply polar covalent. Okay, and a couple more examples here. In each case, which bond is more polar? The bond between B and Cl or C and Cl? Now we don't even have to look at that electronegativity chart. We could simply look at the periodic table, BCl and CCl. Okay, so if I look here, B and Cl or C and Cl, and bear in mind that the trend for electronegativity gets larger when we go left to right, and it goes larger when we go from bottom to top. So if I compare CCl, when I do the subtraction there, versus the BCl, I know that B is going to be a smaller number than C. So both molecules have C in them, so I'm going to be taking this number, subtract this, or this number, subtract this. Since I know B is the smaller number, I'm going to get a larger difference between boron and chlorine compared to carbon and chlorine. So that's quite simply what you can do there, and that's what's mentioned on the next page. Because boron is to the left of carbon in the periodic table, we predict that boron will have the lower electronegativity value, and then chlorine being to the right, and it's the same atom in each of those bonds, it has a higher electronegativity, so we'll get the larger difference there. So if I did look back at that table, I could actually get my numbers. Chlorine is 3, boron is 2, carbon is 2.5, so we could simply calculate that, yeah, between bromine and carbon, 2.8 minus 2.5, I'm going to get 0.3, and over here I'm going to get 0.8, so yes, we could actually work out the calculation and get that value. Actually, it was chlorine, I guess, not bromine. So chlorine, the value is 3, so I'm comparing 2 and 3 versus 2.5 and 3, so obviously, yes, boron and chlorine, I get a difference of 1, whereas carbon and chlorine, I get a difference of 0.5. So, and then that's further work down here, just in the check area. So yeah, checking it out. So boron and chlorine is 1, carbon and chlorine is 0.5, hence the BCl bond is more polar, as predicted from the trend. If you look at the next one, what about PF and PCl? PF and PCl. PF versus PCl. Okay, and from our trend there, so phosphorus is identical to both bonds, but as we go up, we get more electronegative. So the difference between Cl and P and the difference between F and P obviously is going to be a bigger difference here because fluorine has a larger electronegativity value. And of course if we look here again, yes, we can prove that P is 2.1, Cl is 3, F is 4, so yes, I'll get a bigger difference between P and F. So P and F has the more polar bond as predicted. So we could use the trend on the periodic table to figure that out, or we could simply look at the actual Pauling scale there and actually get the numbers there to figure it out. Okay? If I look at this, which of the following bonds is more polar? The bond between sulfur and chlorine, sulfur and bromine, selenium and chlorine, or selenium and bromine? So we could work that out, look at the electronegativity difference. Since we have quite a few different elements here, it's a little bit more difficult to look at just the periodic trend. So using the actual values, of course here I let the answer out of the bag here, but you could take a look at all the values there. So if we look at sulfur, back here, sulfur I had written as 2.5, and yeah, there it is, 2.5. And then bromine and chlorine. So bromine and chlorine, bromine is 2.8, chlorine is 3. So bromine is 2.8, chlorine is 3, and just find the difference. Easy. So 0.5 here, 0.3 here. Looking at the other ones that we have involved here, selenium, Se. If we look back at that, selenium is 2.4. Okay, so selenium is 2.4. Oops, this should be 2.4. And then chlorine is 3, bromine is 2.8. So doing this subtraction here, I have to fix up this because I had it in wrong, which means that's going to give me 0.4. And then over here, so the difference 3 minus 2.4, 0.6. So here we have 0.5, 0.3, 0.4, 0.6. So the most polar bond here would be between selenium and chlorine, because it's the greater difference in electronegativity between the two atoms. So not too bad there, fairly easy if you have that scale. And once again, I will give you this chart, but hey, a lot of the time you don't even need the chart. You just simply look at the periodic properties, increasing from left to right, increasing from bottom to top. Okay, looking at the bottom part here, dipole moments. We're going to skip some of this stuff, but we are going to look at the highlighted areas. So the difference in electronegativity between F and H leads to the polar covalent bond in the HF molecule, as we've seen. As a consequence, there's a concentration of negative charge on the more electronegative fluorine atom, leaving the less electronegative H slightly positive. So we talked about that. A molecule such as HF in which the centers of positive and negative charges do not coincide is called a polar molecule. Thus we describe both bonds and entire molecules as being polar or nonpolar. So, and another way we can show that, so we looked at the delta plus, delta minus. We could also show that as an arrow indicating which way the electrons are going to be spending most of their time. Just like over here, if we back up the truck, over here, electrons are spending more time with fluorine. We can show that with an arrow just indicating the shift of electrons. And the positive, you can't see it well on my paper, but you can see it on yours, the positive here, or the cross, just indicates which end is slightly positive. So shifting of electrons from left to right, and then leaving the positive behind. Alright, in the next video we'll look at the remaining part of this, and we'll see you soon.